Hello? Oh, there it is on. Excuse me. We'll go ahead and get started here. Welcome to the I4 Energy Seminar Series. I'm delighted to present today's speaker, who I've known for a few years, Charlie Huizenga. Charlie is a Cal grad. He received his MS in Mechanical Engineering from UC Berkeley after receiving a BA in Engineering Sciences from Dartmouth College. Charlie wears a number of hats. One of them is here at the university, where he is a research specialist at the Center for the Built Environment and a lecturer in the Department of Architecture. Actually, this is wrong. You're an associate adjunct professor. Yeah, in the Department of Architecture. His research interests include building energy monitoring, design and operation of building energy systems, numerical modeling, building energy use, thermal comfort, window optical and thermal properties, and software development. He is the co-founder and chief scientist of Adura Technologies, which you'll hear about more today. And he's also the co-founder of Agua para la Vida, a nonprofit organization dedicated to providing assistance to rural Central American communities in need of clean drinking water. So with that, please welcome Charlie Huizenga.
Well, can everybody hear me okay in the back? You're raising your hand? Yeah, good. It's a real treat to be here today, and just wanted to say, when I went to graduate school in mechanical engineering, and I was in college in the late 70s during one of the many oil crises we've experienced, and that really got me pointed into this, addressing the issue of energy as a really important topic, and something that became a passion for me. It has throughout my life. And when I came to graduate school, when I was trying to decide where to go to school, I got on the phone and called out to the department and talked to some faculty and said, you know, I'm really interested in energy. Is there stuff going on here? And everyone said, oh, we had lots going on. Come on out. And I sort of made that decision based on that and just the reputation of Berkeley. When I got here, there's pretty much one research project going on in the Department of Mechanical Engineering that really had something to do with energy. There was Professor Greif had a project on thermosiphoning solar collectors. And that was pretty much it. Everything else was, a lot of it was rather unapplied, but certainly nothing having to do with energy. And what that did is actually got me pointed over to the School of Architecture, where some folks, including Ed Ahrens, who I gave a talk earlier this semester in this series, was starting to think about energy in buildings. And now to come back here and just really see the amount of activity going on in the engineering department, particularly with energy, is really just gratifying to see how much interest there is among students, among faculty. And and that interest has really been a huge factor, I think, in a lot of things that have been taking place on campus and statewide and nationwide. So my talk today is going to be about some research that I was doing on campus that spun out into a startup and beyond. And I just wanted to start out by maybe giving hope to some of you who maybe don't have the capital to stream. I certainly didn't start out as a capitalist. I didn't expect that I would end up in the place I'm right now. One of my passions besides energy in buildings is climbing. And this is a picture of a mountain in Nepal called Ama Dablam. And when I was there a little more than a decade ago, I got to tell you a story about a hat. So the group I was with was very, we were into going into the markets when we were walking through these beautiful little mountain towns. And all these towns would have these just wonderfully crafted crafts and handmade wool hats and scarves and gloves and mittens and things. And you go in there, and the tradition for buying something in the market is you ask them what the price is, and they tell you, and you offer them half that much, and maybe a third that much, and you barter back and forth until you get the price you want. So these hats, they usually start out at $5, and so I got a really bad reputation from my group because everyone in the group would always get these hats for $2 or $2.25, and they would say, what's the price? They'd say $5. I'd say, I'll give you 10 for it. I mean, these are so beautiful, and people have just worked so hard to make them, and they're at $10, they're a steal, right? So I would always feel bad about bartering down. So I don't have maybe the genes for being a successful capitalist, but in spite of that, I ended up on this trajectory. So I want to also tell you a little bit about how kind of a little bit of personal history here to maybe just get you engaged in the topic here. This is a picture of a device that many of you probably have never seen, but it's an exercise machine that was developed in the 50s and 60s. Anyone ever have one of these or used one? There you go. So it's just basically it's a big motor, and a pretty powerful motor with a belt on these sort of asymmetric little knobs on the end of it that make it shake. And you just put it on your waist, and it just goes like this. And you can drink your tea, and you can just relax. And meanwhile, you're getting exercise and losing weight. It was just a big thing in the 50s and 60s. Well, when I was 10 years old, we had a neighbor that moved out next door, and this is in the middle of the winter. I grew up in Minnesota, and she was moving into an apartment. She was giving away a bunch of stuff, and she gave me this machine, which I was just thrilled with. I mean, I just loved tinkering with stuff, and this is this really great motor and a powerful motor, big plug. It looked just like this. And I said, well, what can I do with this thing? It's got this motor. I didn't know. Well, I was in Minnesota. As I said, 10 years old. Of course, I played hockey. Everyone does there. So I said, well, what I can do is I can take an ice cream scoop and a hockey puck. I can bolt this thing onto that motor and make this thing throw hockey pucks at me. In practice, I was a goalie on the hockey team. So I could sit in my basement, which is a lot more comfortable than outside when it's 20 below in the ice, which is where we had our practices. And I could put a hockey puck in the ice cream scoop and then hit the switch, and it would whang and throw this thing at me, and I'd do a kick save, and it's practice in the basement. So it was a lot of fun. It worked really well for this, and it was a great motor. But spring came, snow melts, hockey season's over. I said, okay, what else can I do with this thing? Well, one of the things I like to do with my neighbor, I had a friend, we're big tree fort makers. We're always making things out of wood, and we love doing projects. We thought, well, what we really need is a better saw. So I said, if I can just take a saw blade and bolt it on the end of this motor on this thing, we'd have a cheap table saw. It'd be great. We could do all kinds of stuff with it, which caused my dad a little bit of concern. He was saying, well, let's hold off on this for a second. I just got to think about this project. My dad was usually pretty permissive, but even this got him worried a bit for good cause. And he was a doctor, and the next week he had a patient who was, he told the story about it, and this patient is missing his thumb. He said, I cut my thumb off on a table saw when I was a teenager. Whatever you do, you got to stop your son from building his own table saw. It's the most dangerous thing I've ever heard in my life. You just can't. Even real table saws are dangerous enough, but a homemade table saw with a bolt that probably is on the wrong. Like you're supposed to put them, a left-handed thread so it doesn't spin off. I didn't really know that yet. So one thing where I would have started up, this thing would have been flying around the basement. Would have been bad news. So anyway, what he said is you got to get him interested in something else. So he said you got to get him a Heathkit. So this guy went out actually and bought a Heathkit for me. Heathkit, know of Heathkit? You ever see? Is it still around? The company still exists. I have no idea if they do. But they used to make these kits where you could build things out of electronics. And one of the things they had was a science kit for younger kids that you could build a little FM radio or all kinds of different exotic things for 1970. And it was the one on the right. I remember these ads on TV all the time. It was like, I like working with my hands, but I don't like getting my fingernails dirty. That was the big era of electronics. And so they were really pushing people to get into this. And this is probably what launched my career of an interest into tinkering with electronics, which probably led to the project you're going to see today. Now, I'm not saying it was any safer than the table saw necessarily. My dad didn't necessarily see what was going on in the basement, but I can tell you there's a lot of things you can do with an electronics kit that are just as dangerous as a table saw. Now, you guys missing the top here? It's okay, I guess. It's not too critical. But if there's anything that's easy to do about getting the top of the slide on the screen, if anyone can hear me, who knows how to do anything with that, but we'll just proceed. One of the things I just want to point out is some of the really great collaborations that are taking place on campus. And a lot of this as a result of input from organizations like CIEE, who's obviously a big sponsor of CITRIS and I4Energy. I've been working with the Center for the Built Environment, which, as Drew said, is over in architecture, but with CIEE and CITRIS, and now collaboration with mechanical engineering with David Culler, Paul Wright, Chris Peaster, a lot of things going on that were just getting us together working on projects. And that's been really a really great way of bringing together people from all over campus to think about ways of addressing this problem of energy. And so that was a really important thing for me to be able to connect with other people on campus with different kind of thoughts and technology. I'll allude to that in a second. So just to get us grounded in lighting, this is probably something you guys are pretty familiar with, but I just want to point it out because it's just so important. In the U.S., lighting uses 30 to 40% of electrical energy in a commercial building, so it's a big chunk. Buildings use 2/3 of the electricity in the United States. So commercial building lighting is a big piece of this pie if we're going to make a dent in energy and carbon emissions, however you want to look at it. It's really an important thing to get after. And another really important point I want to get across is which one of these light bulbs is more efficient? The one on the left or the one on the right? Any takers here? On the left, right, the good old incandescent. And that's because this incandescent is off, right? I mean, it's not nearly as efficient as this one, but this one's using approximately 0 watts, and this one's using 20, right? And I can't tell you, everyone heard of LEED, the rating for green buildings? Probably have, right? I can't tell you how many of those LEED certified buildings I've been in. We walk into the atrium, beautifully daylit, and you look up and you see these wonderfully efficient compact fluorescent lights burning brightly in the middle of the day when you can't even tell they're on. They shouldn't be on, but they are on. They're efficient sources, but they're not efficiently providing any service. So that's just an important piece, is the way we control lighting is really fundamental to achieving energy efficiency. It's not just about the technology or the source. I guess I can have this. So one of the fundamental problems that I sort of was always kind of tumbling in the back of my head is you should take a standard office building, and you've got it, the thing is lit up, and every single light in there is on, even though over by the window there, it's beautifully daylit, and there's no light needed. Well, in this case, no one's even there, so probably none of the lights maybe need to be on, except for maybe there is someone back here in the corner behind this wall that I can't see, so I'm not likely to turn the light switch off here, which controls the whole floor, because I'm not really sure who's there and who's not. Right? So it's kind of a problem of ownership. Who's going to control the lights? I don't really know what I'm going to do, so I'm just going to let it be. So one solution is to add some chains on these lights and have a pull cord. You can individually control every one of those. It may be not the most architecturally aesthetic solution, although I have seen it. The folks at facility, in the facility plant facility folks here on campus have this down in their office. They've got pull chains on their switches. It's brilliant. I think it's the greatest solution I've seen. Cheap, effective, but it causes some other problems for maintenance, and if you had to actually deploy it in a big building, it'd be a nightmare for sure. So I'm going to tell you. I can turn the sound off here. I don't really want that. Is that easy to do? I won't worry about it. So ignore my chatter in the background. So back in 2004, we built a little prototype using. Some of you will recognize the Mica 2 node up there in this device up there. He's nodding his head. And a little prototype was just a radio and a little power supply and a relay. And this is a little device that I'm showing in this little video here. You can install it in a light fixture in about a minute and a half. This fixture in our office over in Worcester Hall. And by putting it up in the fixture, it's got a little radio, and that allows it to talk to other devices and other sensors and actuators in the space. So here's a floor plan of this office. We put one of these in all the light fixtures, and what that allowed us to do is rather than just have all the lights be on and off together like they normally are, we can individually control those lights. And what that means is that Karen over here, who's sitting in the corner next to the window, can have her light off during the day, especially when she's working on her computer screen. And she actually prefers a little less light. It's more comfortable looking at her screen, which is what most people tend to come to as a normal spot of light level. So, but if she's doing some paperwork, some fine-grained reading where she needs a little more light, she can turn it on. And so she just had control of her light. All we do is say, here, you can control your lights now. Let's see what happens. And what happened was we got a 40% reduction in energy use just from that one move. So it wasn't like we said, here, save more energy. We just said, here, you have control. Use it as you'd like. Use it as you see fit. And that's the outcome. So with that, we got a grant from the California Energy Commission, from the PEER program, to go the next step, kind of a bigger deployment, try to think a little more about the commercial application of this. And we did a bigger installation down on the business services office on a building down on San Pablo Avenue. This was about 2,500 square feet, a much larger group of folks. And we said, now you can control your lights, and you can see in this slide over here, if I click the next one, you'll just see you could individually turn some of those lights on and off above their workstations. And on that space, we saw a 65% reduction in energy use just by giving them control. Same story. We didn't say save energy. We just said, here's some control. Use them as you see fit. And these are just the business services folks, not particularly the greenest minded people in the world, just your average workers, and not necessarily knowing much about energy or electricity. But that's the result. And that's due to a number of things. One is a lot of people like less light working on their screens. Other people aren't there a lot of the time. So now when the morning they came in, they turned the switches on. The custodian used to turn them on about 6 in the morning. All the lights on the whole floor came on for all day until the end of the day. Now, by default, when he turns the main bank of lights on, their lights stay off until they come in and turn them on. And just that alone is a big chunk of savings. So from that, during that project, I got help from 2 Haas students. So Zach Gentry and Josh Mooney on either side of me up there. And they were really interested in the commercialization aspect of this. So they came and said, well, we'll help you with this project. We want to sort of figure out how it works and then kind of look into what the opportunities might be there. So they did that. We put together a business plan. And we eventually entered it into the inaugural California Clean Tech Open competition, which is a business plan competition that's run over in San Francisco. We were the inaugural winners of that in the Energy Efficiency Prize. And as a result of that, we got a package of stuff, some $50,000 in cash, and probably more importantly, office space for a year over in the city from PG&E, and a number of other, like, kind of a startup package in a box, they called it. Just different services and legal services that would help us kind of get the company going. So it was a really big boon to get us going, but mostly it also gave us a lot of validation that other people thought that this had some potential in the market, which is good for our own just momentum and also just in terms of presenting a story to potential investors. So a couple years later, we actually had a product that we developed and had certified for electrical safety, which is no small task, and installed it on campus here at the undergraduate library, Moffitt Library. I'll show you that in a second. So I just want to go through some simple things about lighting, which lighting in many ways is, you can't get too much easier. To figure out how much energy lighting you use, you have one thing is how much light you need, okay? And then you've got to provide it with some sort of source. How efficient is that? So lumens is the amount of light falling from a light fixture or a source. How efficient is it in terms of lumens per watt? And different kinds of lights have different efficiency. And then how long is it on? And that's kind of that simple, right? That tells us how many watt hours of energy we're going to be using. It's much simpler than a lot of things we're interested in buildings, like on the thermal side, we've got some pretty complex heat transfer things to analyze and work out. If you're doing demand response, to figure out how that affect what the temporal issues are going to be. Here it's on or off, or it's at a different level. It's pretty straightforward. What's incredible to me, though, is that if you look at energy standards are actually specified in terms of watts per square foot. So for you engineers about there, what is this? Is this energy? It's power, right? And it's a big difference. What that says is they're really concerned about what's installed in the building. So if you have, a typical standard might be, say, somewhere between a half a watt per square foot up to a watt per square foot of installed lighting. There's nothing in there about how you use it, how you control it. Yet that's such a critical thing. And so one of the reasons I think there's a big problem with thinking about lighting and controlling is that the standards don't really address it very well. They're just talking about what you can install for power. It'd be like having the standard for on the energy, heating and cooling. Here's how big a chiller you can put in the building. We don't care how you use it, but as long as it's smaller or bigger than this amount. But it's not about that. It's about how much energy you're using. And that's a pretty big deal. So add a little exclamation there. So the first question there, how much light? How much light do we need? And that's a really kind of an interesting question. It's interesting to look back in history. Here's a graph showing kind of typical recommended light levels in practice over time. And it's pretty remarkable. This is back in 1920. You've got Ebenezer Scrooge here working by candlelight, doing his accounting, and doing just fine, thank you very much, at something like a foot candle or 1.5 foot candles, right? What's amazing is your eye is able to see over a huge range of light level. You can see in moonlight, which is about 1/10 of a foot candle. You can see in full sunlight, which is 10,000 foot candles. To give you that's 5 orders of magnitude that your eye is able to adapt to. So it's no easy kind of question. So one of the things that's interesting here, in the 50s, the lighting companies, General Electric, those kind of folks, started doing a lot of research, saying, well, more light's even better. It's even better. It's even better. We can double it, install more lighting. This is when the fluorescent technology was taking off. It's cheap. We can get more of these in buildings. And suddenly, they were going through the roof. 100-foot candles we should have in an office. If you've ever walked into an office with 100-foot candles, and there are some on campus, you'd know, and you turn the lights on, it's like, you feel like you're being interrogated. But that's the level that people thought was a good idea. Now, oil prices hit, things kind of drop back down, and now maybe as a typical level, we're looking at, say, 40-foot candles is maybe a typical level for an office design. But what I'd like to point out is that what the right amount of level is really something that only the person in the space can answer. So this is Karen in our first study. She was the one who knew how much light she needed for what she was doing. Right? You can't just say, you want 40-foot candles, and we'll have 40-foot candles for 10 hours a day, and we're done. She might want 10-foot candles right now while she's doing her work on her screen. She might want 70 later when she's doing a contract and trying to read this thing in paper. That's bad copy. You don't know. So it's really important that we have to give some kind of control to the occupant. They're the person that's really going to know what we need, right? What they need for any particular task. So the second thing at the bottom of that equation was how efficient is the source? Lumens per watt. What are we able to provide for lighting? And that's a story that's pretty interesting too. In the bottom here, you've got incandescent. So this is something, incandescents are down in the sort of 15 to 20 lumens per watt range. And no big change over time. It's really just burning a piece of wire in a vacuum, and there's not much that's happened other than adding some halogen in there technology that bumped it up just slightly. You see halogens powdered as efficiency improvement, but it's nothing too spectacular. There's fluorescents here, which are the blue line. are things that really took off, right? And you saw that technology in the 50s and 60s. Through the 60s, really increasing. And today, you've got fluorescent technology, which is, around 100 lumens per watt is kind of the best fluorescent technology. And that's been increasing over time. Most recently, the tubes, if you've noticed them, kind of getting smaller and smaller up in the ceilings. They've gone from like 1.5 inches wide to now they're under an inch to half an inch in diameter. And the phosphors are improving, and that's all getting better. Ballasts are moving to electronic ballasts from just magnetic ballast transformers. The thing that's most dramatic, I'm not going to talk too much about HIDs and other sources like you see in parking lots and street lamps and things like that, but are LEDs. So over here you see the curve for LEDs, which is kind of dramatic here in terms of both in terms of the slope there and where they might get to. So at the moment, there's LEDs in the labs that are pushing 150 lumens per watt now for at least the actual element itself. You have to look at it now, how it comes out in the whole fixture. But you can see that LEDs are on a trajectory here to really, to make a big impact on the lighting market coming soon. So one of the things that's important for controlling them, and something that our approach as a company is taking, I'll get into some of the details of how we do this later, but is that our approach to control has to do with basically turning things on and off with a relay or dimming them with a standard 0 to 10 volt signal, so we can kind of work with all these technologies. We're agnostic to the actual lighting source, and that's a pretty important thing because as things change, or you're trying to do both retrofits and new construction, we need to be able to adapt to different kinds of sources. The other thing about LEDs is efficacy is improving, okay, the cost is coming down dramatically. To give you some context here, this is dollars per kilolumen, and a 60-watt incandescent light bulb is about 1,000 lumens. So think of that as your dollars per 60-watt incandescent. So 10 years ago, we were at $300 for a 60-watt, replacement kind of a bulb, not too compelling maybe as a homeowner. But now you can see we're getting down into this $20 range for that bulb, which is now, given the fact that this is instead of lasting 2,000 hours or something like that for a light bulb, these could last 50,000 or 100,000 hours. It's got a much longer life. This is starting to get starting to get compelling. We're just starting to kind of make inroads. Certainly in places where it's hard to change light bulbs, so you start to see LEDs in places where it's the more difficult it is to access the bulb itself, the more likely you're going to see LEDs right now. But that's changing. You're starting to see now actually fixtures that look a lot like fluorescent fixtures in an office building that are now LEDs. So we've been working closely with LED manufacturers to integrate our stuff right into the LED drivers because there's a lot of efficiency gains and cost gains to be able to do by combining those things. I can talk about that later if there's questions. But I just want to now just step back and think a little bit about the control aspect. Now, control for lighting historically has pretty much been you take two wires and you touch them together and it's on, and you take them apart and it's off. And that's pretty much how it works. So the initial switch, right, the older switch is just this knife blade switch. It's just a wire with a cut in it, right, that you're closing it back up again. Now switches have done some pretty cool things over the time, and those switches were useful for sure. But it's kind of crude control, right? And yet this switch here from the turn of the century is not really any different than what I'll call the modern light switch here, right? Nothing really dramatically different. So what our goal is to really rethink this control issue, change it, and come up with some better ways to do it. So what I want to do is describe a little bit the system that we've kind of got in place, so the components of it, and then go through a few examples of how we use it. So the basic component up here, this controller, is something that you can put in every light fixture if you want, or you could have it could control a group of light fixtures. For example, in Moffett Hall, it's controlling a strip of 6 fixtures, but you could do it however you want. It has in it basically 1 or 2 relays, and it has the ability to put out a 0 to 10 volt signal, which can be used to control ballast that can dim levels. So a lot of fluorescents have dimming capability. They have the 0 to 10 volt signal in. If you put 0 volts in it, it's at its minimum output. If you raise it up to 10 volts, it goes up to 100%. So that's a standard interface for controlling a lot of, and that's the same with LEDs. They have a kind of standard interface for that. We have another device, which we call a sensor interface, which is a device that takes 24 volts in, which is the same thing that powers a motion sensor or a photo sensor. That's how those things are powered today. And then it also takes the output from those sensors. It takes so it can take any sort of 0 to 30 volt signal that might typical of an occupancy sensor or a photo sensor, convert that to a wireless radio signal and distribute that information to the system, so that now all the devices know whether the place is occupied or unoccupied and what the light level might be. The other thing we have is what we call switch interface, which is the same sort of thing, can detect the switch press. Now, what we've done here is rather than sort of invent a new switch, and people, it turns out architects and people in general are pretty particular about what kind of switches go into buildings. We just have a device that you can kind of use any switch with, is the idea. And we use a standard that's called a rocker switch. What do we have in this space? I don't see any here, but a standard kind of rocker switch. A momentary close, you push it and it comes back to the middle. You push it and it comes back to the middle. We can detect that switch press. And then we can turn that into a signal that can be used to kind of do whatever you want to do. It's not actually opening and closing the power to the lights. It's just sending a signal saying this button was pressed. And then through software, we can decide what happens with that. And then the final component is this gateway, which has in it a radio that can talk to the wireless mesh network here up in the lights and the sensors, and then an Ethernet connection so it can connect to the web for the rest of what's going on. So fundamentally, there's sort of a really important paradigm shift that we've introduced with this. And this is the first point I want to really make sure you take away from this. That is that we've broken the connection between how the lighting is powered and how it's controlled. Right? So typically, you've got power going to the lights, and the way you control it is to interrupt that power. Right? And so the way that you've circuited the lights determines how you control it. And we're just changing that. So now you can power them however you want, and you can control them however you want. So let me give you a quick example of that. So if you have a room here that has 9 fixtures in it, normally you've got a switch here. They all go on and off together, right? And that's your only option for light level. In California, you might have 2 switches that allows you to have 2 different levels. But in a lot of parts of the country, you just might have just 1. So with our controllers in there, if you want to just have these 3 lights on here and have maybe the lights that are near the window off, you can do it that way. Even if they're not wired that way, even if the way the switches are wired, it has them going perpendicular to the window or all in one circuit, it doesn't matter. If you want to turn those lights up next to the window, you can do it. Or if you want to have the lights on just over one work area, you can do it. However you're interested in controlling, you can make it work. If you want to dim one light down with this, it has a dimming ballast in it, you can do that. So you've got separate granular control over every fixture. And that turns out to be a really important opportunity for energy efficiency. Think about the use of an occupancy sensor. You walk into a room, the motion sensor detects your motion, all the lights come on, right? You leave, 15 minutes later, they go off. So for some people, that's it. That's the optimal efficiency. But in fact, if you were to walk in that space and maybe have a third of the lights come on, so this is a room that, say, has 70-foot candles worth of lighting. For most of what you do in there, you just want to meet with a few people, talk some stuff over. It turns out that like a third of the light level is actually better. It's a lot more comfortable. You're not just getting blown away by this light. It's actually better. And you're going to, in that case, most of the time, just get away with, say, 30% of the light level in that room. So by breaking it up and have this ability to have granular control, you can get a tremendous increase in the amount of savings over just a standard sort of occupancy motion control. It's not just on or off anymore. It's a kind of a more variable level. So the other thing that this does, by breaking this connection between how things are wired and how they're controlled, is it really changes control from hardware, how things are switched and circuited and laid out, to software. Because now it's all a question of deciding what you want to control, when, and how, and it's all done now in software. So you can make any change you want. If you redesign, if you put a wall down the middle of a room, you can change it. I love this. When I mentioned this competition where we got this office space from PG&E, we walked in there to that space. We moved in. They actually put a wall down the middle of it because we have the energy efficiency prize, and there's a solar company that had won the renewable prize, and they divided it into 2 spots. The way it was wired, when we came in and we turned the lights on or off on our side, it turned the lights on or off in their office. Of course, it used to be one big office. So they had to bang on the door, hey, turn the lights back on or turn them off. And so what happened is the owner of the building sent an electrician into this space to fix it. He was crawling around up above the ceiling for 3 days trying to sort it out because it was an older building, and initially had been changed. There's a low voltage system that was added in the 60s and then redone in the 70s. And he was just up there trying to figure out this rat's nest of wires. And that was something that the owner basically had to just cough up and pay for. So you can imagine the simplification by now saying, well, if you want to just make that switch control these lights, it's just go on the web and remap it. It's just a software change. So it really makes kind of updating, evolving, adaptation a lot easier. Not to mention the kinds of things like, for example, if you want to change something on a shorter time scale, like with schedule, if you want to change the way it operates during the day when people are working there, as opposed to at night when the cleaning crew is there, you can schedule it that way. You don't have to go and rewire the thing in the middle of the night to make that different. You can do it through software. So it opens up a really amazing set of potential. Another thing that's really interesting, I just want to compare, the difference between, say, new construction here at the CITRIS building, and we did the towers in Worcester with our system. When I first started, I was really visualizing this as retrofit. And that's why it's kind of easy to install in existing fixtures. And I think, there's a lot of 80 billion square feet of commercial buildings in the United States. It's a huge amount of energy being used by lighting. And so that's where it's at. But it turns out in new construction, there's a lot of really interesting opportunities there. Mainly, one of them is that in the design process, if you don't have to know how things are going to be controlled ahead of time, it really simplifies the design process. All you need to do is get power to all the lights. You can load up circuits really efficiently, and you don't have to worry there's going to be a wall here, there's going to have to run a switch down this thing. You can push that off later in the design process. And in design, anything you can decisions you can push off later so you don't have to iterate on them makes it a lot better, more efficient, and faster and easier. So there's a lot of interesting aspects of this in new construction, which I think people are starting to get excited about. So I'm just going to touch on the different kinds of control that this enables. I'm not going to go in too much depth. If you have questions, or we can go over this later. I'll be around for a bit after the talk. But the first obvious thing we can do is schedule the lights. So one important thing I just want to get across is that the system is very much a distributed control system. So all the intelligence about how things happen get pushed out to these controllers that are up in the lights. What that means is that if you lose internet connectivity, for example, the system doesn't stop working. It still works. The switches still work. The motion sensors still work. The schedules all still do what they want to do. You just won't be able to change that or control it or see the energy use. But it's all working, all pushed out in a distributed way. So you can schedule things to happen, and the schedule might be turning things on and off. It might be changing the motion sensor delays because you want them to be faster at night when the cleaning crew is there, slower during the day, so you're not turning off lights on people when they're still there. Daylighting is another strategy. So if we have photo sensors, we can measure light levels in the perimeter. We can reduce light level during the day when there's plenty of adequate daylight. Task tuning is an important one, particularly with dimming technology. So when you first build a building or put in, say, new fixtures in a building, over time, the light output from a fixture drops, right? As it gets dirty and the lamps wear out, that changes. So what that means is that designers, when they first put these fixtures in, they over-design them by about 20 or 25%. That way, by the end of their life, you get down to this minimum level, which is this target, this sort of changing curve that we looked at earlier. So who knows what that should be, but they multiply it by 1.25 anyway at the end just to be safe. So what that means is when you put in new lights, why not just bump that down by 20% to start with? And then as the lights get dirty or things change, over time, if you need more light, you can always raise it back up. So by having this software change, the way it used to happen is a lot of ballasts had this ability to do this tasking, but it meant you got on a ladder, you got a little screwdriver, and you adjusted a little set screw, a little pot on the ballast, right? Who's going to do that? And run around to the whole building and do that every year or something like that? It doesn't happen, right? But now that the software changed, it's easy enough to fix. So that could be a huge thing. We just did a project at the Pleasanton Library. They put dimming ballasts in the whole library, and we just started off the top. We're going to go to 80% because they were new fixtures. They were overlit. They had plenty of light at 8%. They're happy with that. That's a big savings just every day. That's just kind of off the top of all the other strategies that we're doing. Motion sensing, I talked a little bit about that already. Personal control, which is sort of our initial impetus for this, just letting people be able to turn the lights on and off. And then demand response, which I think you've talked a little bit about in the series before, but the notion there of when the grid is in peril and we need to reduce our energy use, lighting turns out to be a really great fit for that because lighting it is what it is. You turn the lights off and they're off, and you turn them on and they're on. There's no weirdness about thermal lag or estimating what impact that might have, and so it's a really great resource. It's a 30 to 40% of the electric load of a building, so you can make a big impact there if you cut off, say, half the lighting, which often you can do in a building without much trouble. So there's a lot of great opportunities there for demand response. The other really important thing that's different about what we're doing, which I want to emphasize, is that we're actually measuring energy use at the point of control. Every one of these controllers has a current sensor and a voltage sensor in it, so we can measure energy use right there at the fixture. So what that means, we're able to aggregate and tell a really interesting story about where the energy is being used. It's very easy to aggregate lots of data points up to tell a story about what's going on the building. It's very difficult to disaggregate data from a building meter, read once a month in some cases, and figure out what's contributing to that. So by building up the story about both spatially and temporally where the energy is being used, you can really do some interesting things. So all this data is being collected then comes back to our website, And here's our kind of the main dashboard in this. And so what you can see from that is the blue line here is the energy use on our office. The green behind it, I'm not sure if you can see that, but that's showing you how it was controlled before we installed our systems. Before we put it in, it was just a schedule, came on at 7 in the morning, went off at 8 o'clock at night. That's just how it operated. So now we can track exactly what the savings are, dollars or kilowatt hours or tons of carbon, whatever your favorite metric might be, and do a lot of interesting analytics with that. So you can just have an easy kind of a Google Outlook kind of schedule to schedule what the lights do, how they behave. You can create a new event that could be weekdays or weekends, repeating all the same kind of things you do for just any scheduler. You can use now to control the lights. With the demand response, the same sort of thing. You can have you can create a manual demand response event where you say you get a call from the utility, say tomorrow we're going to have an issue. We want you to shed load starting at 2 o'clock in the afternoon until 4 o'clock. Or you can tie into an automated demand response system that automatically gets a signal from the utilities saying we need you to cut load, and that just automatically triggers the new behavior of the lights. And then personal control is enabled either through the website, you can do either a widget on your desktop or through a web page. You can control lights just like any switch, or you can have that running on a smartphone. So now that control to a smartphone is now happening through the web interface, through the gateway, and then out to the lights, so you can control them just like you could with any switch in the space. And that's customized for the particular person who logs in, and their login determines then how that switch maps to what lights in their space. And then on the website, you can also get a much more detailed. This is an office installation downtown San Francisco. So this is a pretty big floor plated building. You can see every light, what its status is. Here's an aux sensor. This space is occupied right now. It's green. This one's unoccupied. The lights are off. It's red. You get feedback about the system. You can click on one of these lights and control it, adjust it if you have access to that. So a facility manager might be able to control any light in the space. If this is your office, you might be able to see what's going on in the whole space, but only control it in your office. So all those levels of what you can see and what you can control are managed by kind of a security system login. We also have some pretty interesting analytics you can do by drilling down and seeing. This is a pie chart showing you where the lighting energy is being used by space. And I can click on one space and then drill down to the next level. Which rooms in that floor, for example, are using most energy? So if you're looking at it, you go, wow, why are we using so much energy now? You click on the graph there. It gives you this distribution. You can click on that, drill down, and see where it's going. We call it kind of a what's on report. It tells you what's on, and it tells you why. In this case, these are the things that are on right now, and they're on because of an occupancy sensor. So that's what triggered them to come on. So a really useful diagnostic tool to answer questions, why is energy what it is right now? And then some applications which have nothing to do with energy. This is one where we can provide folks with information about space utilization. So how often was a conference room used? And it turns out that a lot of people who have big campuses are pretty interested in this question. How many small conference rooms do we really need? We're giving up space for those, but we really don't have a way of knowing how often they're used. You can provide a report for how often they're being used, what kind of conference room is being used as a way of providing feedback to them for how they should manage their office space. And then, since we're measuring the energy use at the fixture level, we can also detect if there's a failure, if a lamp burns out or a ballast fails, we know it, right? So that's useful for both maintenance, so we can provide a report on what fixtures are out, and the maintenance folks have a list of what's wrong. They can take the right stuff with them, go to the building to replace it. So it's a really useful thing for maintenance. And then finally, it's the ability to compare spaces. You can compare a space with another space. You can compare like how we're doing this month versus last month, or this year versus last year, just to sort of do some comparisons, which are often interesting from an energy perspective to see, are we getting better, are we getting worse? How's this floor comparing to that floor? How's this dorm doing against that dorm? Whatever kind of competitions or anything you want to have. Another thing I want to just point out is how important it is to actually measure energy use as opposed to just kind of use a proxy, which is what most systems do. So this is generically what happens with a dimming ballast. You've got this 0 to 10 volt signal in which you put a 0 volts or 10 volts, and this is percentage here. The light output goes from some minimal. They don't go down to like 0%. They usually go down to maybe 3 or 5 or 10% is the minimum. And then it goes up to 100%. And so this is the light output. Over here is how much power it's using. So generically, as you use more light output, you have more power, and this thing dims down. Well, in reality, when we measured in the field, this is what we're getting. This is some data now from the Pleasanton Library I mentioned where we put these dimming ballasts in. What's interesting here is a couple things. One is, obviously, they don't go down to 0 when you've got the bottom load here. And you might note here that they're using about 25% of the power down here at about 5% of light output. The other thing is this little blip here. And this isn't, when we first measured this, it came about like this. They said, well, we want to run at 80% for this tasking I mentioned. So we set them to 80%, and they were using about 93% of the energy. And we said, well, that's weird. Something's amiss here, right? And we looked into it, and what we found out in talking to ballast manufacturers, for this particular ballast, what happens is, as it dims down, there's a point where they turn on some little filament heaters in the lamps. Because as you get to lower dimming levels, you have to provide this to make the arc work properly, to make the lamp function properly. And this is the point where that thing turned on. It just so happened that when we went to 80%, we hit that point, and boom, that thing turned on, and that's on all the way down to here. So by changing that set point from 80% to 81%, suddenly we're saving our 19% energy as opposed to 7% energy just by making that subtle change. That would never come up if you weren't actually measuring it. If you're just saying what a lot of light systems might do, say, well, you're at 80%, you're 80%. That's what the light output is. But in fact, it's nothing to do with the actual energy you're using. So just a point to emphasize how important it is to measure things. The other thing is that this curve now, this black curve is now the efficiency, that same scale, relative efficiency. So if I say it's 100% here, meaning that's the efficiency when it's fully lit. So that's its nominal efficiency. As you dim it down, it gets less efficient because you're kind of burning this power that's this sort of, think about it as this sort of a standby power, it's extra power for the ballast. You can see that at this point when you're at the maximum dimming level, you might not remember this exactly, but the chart I showed for the lighting efficacy, I said fluorescents are sort of 20 lumens per watt. I mean, incandescence 20 lumens per watt, fluorescence about 100. It's about a 5 to 1. Fluorescents are about 5 times more efficient than incandescent. Well, with this fluorescent dimming ballast, when I'm dimming down to the minimum 5% level, you can see that 20%, that's about the same as an incandescent in terms of efficiency. So as I'm dimming down, suddenly I'm getting a lot less efficient. Not saying it's a bad thing. I'm saving energy here for sure. But it's interesting to note that the efficacy changes dramatically. One of the exciting things about LEDs is that they offer a much better ability to be, some of the LEDs actually get more efficient as you dim them, the actual device itself. So there's a lot of interesting opportunities there for dimming when we start realizing more LED fixtures. Okay, so I'm going to go through a couple of examples of projects we've done. The very first project we did was Moffett Library. That building was built around 1960. That was a time when the slogan from the utilities was, energy is going to be too cheap to meter. And what they meant by that is, you probably just don't worry about what you're putting in because we're probably just going to charge you a flat rate for your electricity. It doesn't matter how much you use. It doesn't, just to connect it, it's going to be so cheap we won't even bother metering it. That was actually a concept at one point back then. And this building kind of reflects it. The initial lighting, you can see the lights going across here. This is today. When it was first built, there were lights going this way as well. And those are on. And they're also, had a higher output than the lights that are in there now. So the lighting was over twice as bright as it is now. It's already pretty bright in there, if you ask me. And the control for that was via the circuit breaker. And the circuit breaker is located in a closet. And the closet is locked. And the only person who has the key to that closet are the electricians that don't work in that building. They're central electricians. So the lights 24/7 since 1960 have been running in that building. It's kind of mind-boggling, but this is all over the place. So in that case, we put our controllers in, and just at the end here, we control each strip individually. Rather than putting in each single lamp fixture, we just control each strip. But that allows us to put every other strip on for 50% control. So what we're about to do now, we're kind of doing a new phase. We're going to put motion sensors in these study areas. And so if no one's in the study area, we'll drop the light to 50% in those areas. At night, for the custodians, they can clean easily with 50%. So we're going to either squeeze some more savings than we already got. So in that case, we had 100 megawatt hours per year savings, and that's a little under a 3-year payback. But with the rebates from utilities, who are obviously encouraging these programs, that ended up being an instant payback. We also have controllers in the reading room at Doe Library. Beautiful room, beautiful vaulted ceiling. And these are skylights at the top. Really what it is that it's a vault, it's an open space above there, and with some big, powerful, high output fluorescent lights in there. And the idea is at night, it kind of simulates light coming through those skylights just like it does during the day. During the day, you cannot tell those lights are on. You turn them on and off in the day. We put the controllers, they have to just kind of squint. Oh, yeah, they're off. You can barely tell because it's just so bright and it's flooded with daylight. To turn those off, you got to go out here, up the stairs, out this security door, up a ladder, across this kind of chasm in the roofs, and then in a roof entrance in the roof in to get to the circuit breaker that controls those lights. So again, those have been on for I don't know how many decades, right? Burning straight. So we've now got controllers in those. So these are a couple examples of on campus where we've done it. We've also recently been doing some interesting projects in parking garages. This is downtown San Francisco, Anchorage Square, using motion sensors and daylighting in parking garages, which normally just have their lights on 24/7. And there's huge opportunities there. So again, some pretty quick paybacks and some interesting projects. This is another downtown building downtown San Francisco. We've got now we've done the parking garage, and we're starting to do some of the floors in the office building here as well. Again, relatively quick paybacks. Interesting anecdote here from parking is one of the concerns they had initially by us sort of lowering light levels. They're really worried about safety. And they say, you know, we're not sure we really want to reduce light levels because people aren't going to feel safe going to their cars and security. And what they came back to us after the project and said, you know, this is the best thing that ever happened. Because what happens now, they have a bunch of security cameras in there, and some guy in a room, the guard, is watching these monitors, right? And he's kind of, you know, half paying attention, half doing, you know, watching the game or whatever he's doing. But now what happens is when someone walks into a certain area, the lights brighten up. And if you ever look at a video camera, you know, when the light gets brighter, it takes a little while for the iris to adapt. So when it gets really bright at first, and then it kind of adjusts. So what happens when someone walks into space, it kind of flashes, and it immediately draws this person's attention to that camera and to that screen, and they're watching who the person is there and why they're there. They said they're really excited about it's totally unanticipated, but an advantage. So they were actually excited about the security thing. It's been an improvement in safety rather than a detriment. You never know what's going to happen in these things. So I won't dwell here, but since we started out, we've been starting to get some traction. Now we're up to, I think, 4 million square feet of installations. It's still modest by some standards, but we're starting to get somewhere. But I wanted to spend a couple minutes and gotten some recognition here and there from some words. But I want to just quickly go through a little bit of my experience of how we got from this idea to this company. And when we started out winning this this business plan competition to actually becoming a funded company. I'm going to move real quickly here. So one of the things that's pretty interesting here, this is investment in clean tech from venture capital, and you can see it sort of nibbling along here, and then really taking off, in the middle of the last decade. So this is when we started right here. Going, wow, this is where we want to be. We're starting to see the interest in clean technology, highly variable, of course, as you can see, a lot of changes there quarterly. We're going to go after this, and so my experience was really writing grants. Right, and from an academic perspective. And in that scenario, you're writing a 50-page proposal for, say, maybe 50 or 100K, or maybe more if it's a big grant, and you got maybe a 25% chance of getting it. That's the sort of rough experience that I've had in grant writing. Now with venture capital, it's a little different deal. You basically you have a slide deck that has 3 slides in it, okay, and of which you're going to show one before they interrupt you and not let you get to the other 2, and then you're asking for like $5 million here, and it's called an ask now. It's not a proposal. This is called the ask. What's your ask? That's what they're going to say to you. This is a different number than I'm used to saying, and then the probability here is a little different too. Is that we had to go through a lot of people, tell our story over and over again, show that slide deck of 3 slides over and over again, and people. The other thing about them I should mention that investors never say no. They say, that's interesting. We'll think about that. They just don't say yes, and so you get strung out forever by these people trying to tell you what to do. Eventually, we were able to, make some progress. But the thing that for you, maybe a bunch of engineers, and maybe I'm wrong, but I was excited about the technology. I mean, this is the greatest thing. It's going to make a big difference. We're going to save kinds of energy. I've got to tell them about what I'm saying up here. Is these are the top 3 things that the venture capital investors are interested in. So I'm thinking going into this, that technology is number 1, right? Well, it turns out it's not number 1. It's really the first thing they're interested in is the business model. And can that give them a great return quickly, right? So I'm thinking, okay, technology is the second most important thing, at least. That's not bad.
The people is number 1.
What's that?
The people is number 1.
The people?
Yes. Who's starting the company?
Great. The people is number 1. We'll keep that in mind. Maybe we'll get up there. So, but it turns out technology is not number 2 either. So the first one is the business model enables a really great return really quickly with great people. And the business model's got to be scalable. And then the technology, I'm thinking, right, is the third, at least, most important thing. Well, after going through this process for a couple of years, it turns out that it's actually the exit strategy is the third one, right? And the exit strategy here is not, which sign you're looking for in the fire. This is how are we going to get your money out of the thing at the end of it? How are you going to sell the company, or who's going to buy it? And the technology ends up being there somewhere down on the list. And I got to say that my excitement dwindled on that part of it. I stopped talking about it at one point. But an interesting thing, I think, from the academic side of it is just to look at the relative investment here from our initial funding from CIE, CVE, the Energy Commission, of a little less than $200,000 from this technology. And at this point, we've got investment on the private sector side of $17 million from venture capital. It's really pretty great leverage of public funds to get some technology like this into the marketplace. So I think that's a great part of the story. I just want to leave you with the title on this slide. It says, "Wireless always wins." And I think we've seen that time and time again. Every time wireless technology has come up against wired technology, it's pretty much won, right? And this is a little story. I tell you, this is my friend Pedro Zamora, who I work with in Nicaragua. He's a mason for this organization. Teresa mentioned we build drinking water projects there. I've been known him for 20 years, and he works on projects, and so he'll go out and he'll be in a project for like 2 weeks at a time. And these are small projects. I mean, even the big city where we have our office, when we started there, it had one phone and it had a crank on it. And you went into the phone office and you go, Matagalpa, Matagalpa, ring. And then they say, it's not working today. And you come back the next day. That was the level of phone service in the city where our office was. In the communities where we're doing projects, there's no electricity, nothing. This guy now, as of last year, they have cell phone service there. They've skipped the whole infrastructure of normal phones. And now he's got a cell phone. And when I first saw it, I was kind of blown away. This is crazy, but it's the best thing that's ever happened to him. Now he can go for 2 weeks, work in the project. He can call his wife every night, who's not in very good health, check in with her. How's it going? It's made a huge difference in his life. And so, wireless is going to win. And in buildings, there's no difference there. I mean, it's cheaper, it's simpler, it's easier to do stuff with, it's easier to retrofit. It's going to happen. And so, I just want to leave you maybe with this one last notion of a final shift here, which hasn't happened yet, but which maybe would hope might happen. And that is because we've been working on these wireless sensor networks, how to deploy them in building. And what I would offer you is that lighting is the perfect platform for this because it's ubiquitous. It's all over the building. It has power going to it. And it's just sort of a natural place for this infrastructure for sensing and control to reside in a building. And so the vision that we have as a technology that this could eventually become the mechanism to have additional sensing and actuation going on in a building and provide this platform to take us to the next level of control in buildings. So I'm going to end with that. Happy to stay after. I know we're getting short here, but take any questions if we have a chance for one or two now, and then I'll stick around afterwards.
Are there any questions?
Yeah.
Is this on? Yeah. You've been talking about control over lighting, but only over the intensity of lighting, the on, the off, and the in-between. But there are other attributes of lighting that people might want to control if the technology would permit, such as the directness or indirectness or the color rendering, and generally the quality. Does new lighting technology offer the promise that those aspects of control might also be delivered to the end user? And if so, will the opportunity to control more attributes create complexity in the control interface, which might also be a challenge?
Right. That's a great question. So there's kind of two aspects to that, or at least in my answer. So one of them has to do with changing the quality of the lighting. And one of the ways that we can do that now is we actually have some installation we've done where in general, to simplify some things here, there's kind of two forms of lighting that's used in commercial buildings. What we'll call direct lighting, where you have a fixture shining light right down on you, and indirect lighting, which is bouncing things off the walls. And so in this space right now, we've got mostly direct lighting happening. We've got lights above us, and these sconces a little bit lighting up the walls, so there's a little aspect of indirect lighting with that. One of the things we've done in some projects is there are some fixtures which have some light that shines directly down, and other light that's above, on the top of the fixture, that lights the ceiling for indirect. And so you can gain independent control of those two ballasts and then change the qualitative aspect of the lighting with the control we have now. And that's something that, by independently controlling those two levels. The other thing which you're asking about, other things we're going to control, particularly with respect to LEDs, I'm sure what you're thinking about, LEDs offer the potential to change the color output of the device. You can change the spectral output of LED. And that's going to offer some really interesting opportunities. So a couple of things that impacts. One is that your eye has a certain sensitivity. It changes with spectral, right? With spectrum. A lot of people have looked at if we move towards bluer light, you could actually lower light levels a little bit because your eye's a little more sensitive to that than it is on the orange or redder side of things. So we could actually potentially have increases in efficiency by changing that color. The other thing that's, I think, a fascinating topic is we've evolved to have this sort of a change in color throughout the day. The light levels outside change from sunrise through the morning, the afternoon, as it's sunset. There's a spectral change that happens there. So people are interested in this idea of trying to mimic that, or at least use that color to sort of set the mood or the ambiance of a space. So we've been working with LED manufacturers, as I said, to integrate our control right into LED drivers, and that's certainly one of the things that we're looking at is how you'd be able to set color. And the control for that is essentially going to be like it is, any digital kind of control. It's going to be like, think of it as RGB kind of control, and you can now set. It won't be as infinitely controllable as it might be on your monitor. You're not going to have necessarily 65 million colors to choose from, but essentially it's infinite, and it's an analog thing. You can adjust. So that's something that's definitely going to happen. I think it's really exciting. Is it going to make it more complex? Absolutely. But I think the opportunities are so interesting that it's going to be a compelling direction to move. Yeah.
How are you handling wireless energy? How are you powering the sensors wirelessly?
Right. So Al's question is, how do we power these devices? So there's a lot of different answers to that. The basic infrastructure for our devices, these controllers, are in the lighting fixtures. So we just connect there and use the power from the high voltage. Or in some cases, there are, especially with LEDs, now there's low voltage, 48 volt and 24 volt distribution systems. But any of that stuff is fine. So our controller has this universal power supply, and right now anything between 90 and 300 volts is fine. Most lighting systems in commercial buildings are 277 volts. Probably haven't run across that. It's kind of a weird voltage. It's a 483 phase kind of single leg thing. Unless you go to Canada, in which case it's 347, just because they're a little different up there. But that's easy. That part's done. The sensors are more difficult. And so with sensors, there's two ways we power those. One is by attaching some device somewhere to power that can generate the low voltage to power the sensor and running low voltage wires. And that's how it's traditionally done in most spaces now. It has been done historically. And the other is to start to use energy harvesting devices. So we have, for example, an interface in our system on the market now you can buy motion sensors that are powered with a little photovoltaic cell on them. And so they have a capacitor essentially, and they can charge up when the light's on the space and get enough energy to send a small radio signal. So we have our sensor now has an interface to that. So that takes a radio signal which is different than our standard one and converts it to our network and can distribute that. And then there are also, for switches, we have an interface to devices that generate power when you push the switch. You can generate either through electromagnetic impulse or some are piezoelectric. You can generate a little bit of electricity with the switch press. So you can make the switch generate the power for the device. In general, I think moving forward as we get more increasingly ubiquitous sensors, that's going to be a critical aspect. At the moment, it's not necessarily driving what we're doing in practice, but I think as we try to increase the density of sensors, it'll be increasingly important. One thing we're not doing right now is using any batteries in any device that we put out there. That there's been a little bit of resistance to that in the commercial building sector to have to be able to change batteries. So at the moment, the only device, I say with one exception, the only device we have that takes batteries is a remote kind of device, a handheld thing. And so that it still has like a 5 or 7 year battery life. It seems acceptable to folks, but it's also a little easier to manage. And it can also, the good thing about a wireless device is it can tell you when the battery's getting low. That can show up on the website. Oh, by the way, the following devices are down. You might start thinking about replacing the battery in those. So. Any other questions? Great. Well, thanks for your attention. Enjoy lunch.